that deals with twin primes. Now we're stipulating that q and q plus 2 are both prime. We're supposed to show that the sum is divisible by 12. Now a more convenient way to write this might be to write this as 2 times q plus 1. Right, because that's clearly what that's equal to when you just factor out a 2. So that's 2 times q plus 1. And so right here it would be enough to show that q is a q plus 1 is a multiple of 6. Okay, multiple of 6, which will be sufficient, which is what we're going to demonstrate. Of 6. Okay, and y'all, my q there looks a little like a 9, but that is a q. Now I have a couple of examples here, like for 5. 5 plus 1 is a multiple of 6, 11 plus 1 is a multiple of 6, and so on. Now, I'm going to establish a little result here that really is very, very helpful. This says that for any prime greater than or equal to 5, notice this result doesn't work for 3 and 5, so we have to start at 5. But for any prime greater than or equal to 5, p cannot be congruent to 0, 2, 3, or 4. Now, if p were congruent to 0, it would be divisible by 6. That would say that p minus 0 is divisible by 6. So we'll rule out that case without showing any work. And this is just an example of how a proof would go for any of the cases. If p is congruent to 4 mod 6, that means p is equal to 4 plus some multiple of 6. You can factor a 2 out of there to get that 2 divides p, which is certainly a contradiction, right? A prime number is only divisible by 1 in itself. So this is definitely true. For all prime greater than or equal to 5, that prime cannot be congruent to 0, 2, 3, or 4. That only leaves these two choices down here. That only leaves these two choices. We can't be congruent to 0, 2, 3, or 4. So since there are an infinite number of primes, they have to fall into one of these two classes, 1 or 5. Okay? Now again, I wrote this down again, but in case 1, if q is congruent to 1, okay? And remember, q is a prime, and so it has to be either congruent to 1 or 5 right down here, right? So that's what we're doing here. There's only two cases. Now, q congruent to 1, if you add 2 to both sides, you get q plus 2 is congruent to 3. But remember, q plus 2 is a prime also. Remember, q plus 2 is posited to be a prime number just at the very beginning of the problem. It's part of the twin primes, right? So q plus 2 is prime. Right? And since it's prime, it has to be congruent to 1 or 5, right? But right here we have it's congruent to 3, so that's a contradiction. If you look at the list of numbers, that this case doesn't work anyway. Now let's take a look at the case q plus 5 is congruent, q is congruent to 5. Okay, and that's the other possibility here. If q is congruent to 5, that's the same as saying it's congruent to -1, because 5 minus -1 is 6. Okay, now again, if this also implies that q plus 1 would be congruent to 0, right? Because if you add -1 to both sides here of this congruence, you get q plus 1, and a 0 would be right here. Okay, so that says that q plus 1 has to be divisible by 6. In other words, this says that q plus 1, this is equivalent to saying that q plus 1 is divisible by 6. We'll just say it like this, folks, that 6 divides q plus 1. Okay, that 6 divides q plus 1. But that's what we set out to prove, because if 6 divides q plus 1, then this would be equal to 2 times. This would be equal to 2 times some multiple of 6. Some multiple of 6, which is certainly a multiple of 12, right? Which is equal to 12 times some other constant, some other integer. That would be equal to 12 times some other, we'll call it m sub 1 if you want to. So y'all, we proved what we set out to prove, that the sum of two twin primes has to be divisible by 12.